if we are visualizing in the structure 1, hello everyone, welcome back to PLUTUS STEM. So today we are going to discuss a very important concept of organic chemistry, that is resonance effect. So we have already covered up the various other important effects such as inductive effect, electromagnetic effect, hyperconjugation. So this is a very important effect, the resonance. So why we are going to study this, and what are the phenomena which are occurring over here, and what are the possibilities, what are the stabilities, what are the effects which we are going to see in this. So today we are going to start with the basic thing, why we need this resonance. So actually the starting of this resonance came from the very important compound benzene. This is our benzene compound, and it is having a single bond and a double bond. If we visualize the structure of this compound, let's say 1, 2, 3, 4, 5, 6. So this compound, by visualizing the structure A, what we can assume over here, that it consists of 3 single bond and 3 double bond. 3 single bond and 3 double bond between carbon and carbon. So we can assume that all these 1, 6, 2, 3 and 4, 5 carbon, they are having double bond. They are having double bond. And we know the bond length of this double bond is nearly equal to 134 or 136, nearly something. And if you see the single bond, so rest of the like 5, 6, 1, 2 and 3, 4, 5, 6, 1, 2, 3, 4. Sorry. 1, 2, 3, 4, 5, 6. So these are all single bond, and we expect that they all must have a bond length equal to 156. The bond length must be nearly equal to 156, and we are going to assume that in this molecule we are having two different type of bond length. But as been studied by some new techniques, X-ray, XRD, etc., we came to know that this benzene ring doesn't have this neither this 134, neither this 156. The bond length of this benzene ring was in between these two values, and all these bonds, they are having the same bond length. So why this thing is happening? So we are unable to explain the structure of this compound, the properties of this compound by this single structure. Because if we are seeing the single structure, it is having two different bond length, but actually it is having only single one type of bond length. And by this single structure, we assume it is having either this bond length or 156, two type of bond length, but actually it is only having one type of bond length, and that value is neither 134 and nor the 156. So that is in between both two values. So to explain any compound, if we are unable to explain any compound, on the basis of single structure, we need more than one structure. Such compound, they are being termed as such phenomena through which these structures are being performed, that is termed as resonance. So this compound is being like over here like this. So in this case 1, 2 is double bond. Initial case 1, 2 was having single bond. So we can assume sometime it is in this state, sometime it is in this state, and these two structures, they are being separated by this arrow, two-sided arrow. And These two are hypothetical structures being assumed by us. The actually the compound, the real structure of compound is something like this, and that is termed as resonance hybrid. That is being termed as a resonance hybrid. So this all thing was just how this resonance originated, because we were unable to explain any compound on the basis of a single structure. That's why we perform a resonance structure by moving a pi electron. So we can see what is this resonance phenomena. The resonance phenomena is the delocalization. So in the first slide, we have studied why resonance. And in the second slide, now we are going to see what is the resonance. So in that slide, we have just covered up why we are studying this resonance phenomena. And now we will be seeing what is a resonance phenomena. So the delocalization of pi or lone pair of electrons. Delocalization of pi or lone pair of electrons. This is the very simplest definition. The simplest definition of resonance is delocalization of pi and lone pair of electron. So whenever you see the delocalization of pi bond or delocalization of lone pair of electron, you can assume that there might be the phenomena of resonances occurring over here. So there are some necessary conditions are there. All the movement of this pi electron, all the movement of pi electron or delocalization of pi electron is not being considered as a resonance. So there are some conditions which we are going to see over here. What are the necessary conditions when we will see that these movement of pi electron and lone pair is considered as resonance, and some movement we will see that that will not be considered as the resonance. The first thing is movement of pi electron, or you can say movement of only pi or lone pair of electron. In this case, we will not see no movement of sigma electron and no movement of sigma electron and atoms. So what is the difference between 1 and 2? So I will show you by a simple example. If we are having a molecule like this, if we are having a molecule like this, better will be like this. This is a compound, this is a ethanol compound. This is a ethanol compound, and if you see in this compound, movement of pi electron like this, movement of pi electron like this. So then you can say that over here H C H C O negative and C positive charge. So in this case, we can see the movement of only pi electron and lone pair takes place. So over here, the movement of pi electron is taking place. So we can say yes, this is a resonance phenomenon, and these two are resonance structure. These two are resonance structure. But if you do something like this, if we are doing something like this, the movement of this hydrogen, in this case, if you visualize the case number 1 and case number 2, product number 1 and product number 2, in the one, all these atoms are situated on their original state. Only the movement of pi electron takes place, but in this case, the movement of atom also takes place. So this phenomena is resonance, but this phenomena is not resonance, but we know it is a tautomerization. It is a tautomerization. So the main difference over here is no movement of atom takes place. And we have all told you the no movement of sigma electron. Sometimes the movement of sigma electron takes place, and that give rise to hyperconjugation. That give rise to hyperconjugation or no bond resonance. So if you are not familiar with what is the hyperconjugation, what is the no bond resonance, so you can watch our previous video in which we have discussed regarding the hyperconjugation in quite detail. So over here this phenomena will be cleared very much. So the difference between this resonance and hyperconjugation has also been explained over there also. So you can watch over there also. So the one thing which we have seen over here is only the movement of pi electrons and lone pair takes place, no sigma electron and hydrogen atom or any atom movement takes place. And if you see over here, but the second point is, second important thing regarding these resonance structure is that we are seeing over here, that would be better over here only. Oh yeah. In this structure, if you see, and so this is resonating structure 1 and this one is resonating structure 2. So these two are resonating structure and these resonating structure they are hypothetical. These two are hypothetical. These structure are hypothetical. So those structure which we are drawing they are hypothetical, which means they are not the real structure of the compound. So for real structure we draw the resonance hybrid. So while drawing a resonance hybrid, you have to make all the bonds which are not moving. So this CH3 they are intact in all these resonance structure and this bond. So the only movement takes place over here. So that is being represented by the dotted line and the atom this is being termed as partial negative charge and this one is as partial positive charge. So this is the resonance hybrid and it is more near or closer to real structure. This resonance hybrid is more closer or near to the actual structure of the compound. This is being more near to the actual structure of the compound. And the important thing regarding over here will be that net charge on the compound of the compound remain constant. Net charge of the compound remain constant. The net charge which a compound is having that is going to be constant, which means we are not going to deviate the net charge of any compound. If it is having -1 charge, so throughout all the resonating structure it must have a -1 charge, and if it is having a +1 charge, so throughout the whole structure it is going to have a plus charge. So this is the way, or it is having a one free radical, one free radical present. So throughout the whole structure, which we are going to see that one free radical must present, only one free radical must present throughout the whole structure. So for net charge, you see the previous example only we are going to discuss. So if you see in the structure 1 and in the structure 2, If we are visualizing in the structure 1 and structure 2, so net charge over here is 0 because all atoms are neutral, so there was 0 net charge. In this -1 +1 plus minus, again it is going to be 0. So both the structure they are having the net charge equal to 0, which means the net charge on the compound remain constant or same. So that is also a necessary condition. And whatever the structure which we are drawing, they must be of the comparable energy. The energy difference between those structures not be of a great difference. The energy difference should not be of a great difference. So these are some basic points before going to the drawing. Yeah, another example, if you see over here, CS2 double bond C, single bond CS2. This is a free radical. How we can draw a resonating structure of this? Like this. So these two are resonating structure, and if you are only doing this, so in this we are having three radical. In this one free radical, in this one free radical, in this three radical. So this is not a resonating structure. The free radical or charge must remain same throughout all the resonating structure. So it is being represented like this. So this radical coming over here, this is going over there, and they are forming the bond, and this is remaining the new free radical. And if you draw the resonance hybrid of this, it will be like CS2 single bond CS single bond CS2, partial dot over here and partial dot over here. So this is the way how we can try to draw this structure. And one more thing I will tell you over here only, the octet must also be, octet rule must be in consideration. The octet rule must be in the consideration, and those compound they belong to the second group like carbon, nitrogen, they must have not exceed their valency more than 4, because they are not having the energy of the orbital quite similar to the p orbital. That's why they will only be tetravalent. All the second period element are going to be tetravalent. If by rotating the electron we are making them the pentavalent, that is not accepted in this formation of this, you can say, resonating structure. So what are the different ways through which we can form these resonating structure? So one way will be pi bond and pi bond. So in this type of movement, we are going to see that one pi bond will be moving with another pi bond. So movement of only both the type of movement we are going to see will be the pi bond and pi bond only. So this is the compound, this is the original compound. Over here a positive charge, over here a new bond generation, and over here a negative charge generation. This thing, and another possibility, again it will goes back. Actual structure like this, and it can also move in the opposite direction. Like this. So the movement can be on any side, either the right side or the left side, because both the element they are having the similar type of electronegativity. If we are having a group like this, Over here, the flow is going to be towards electronegative atom. Flow of electron should be towards electronegative atom. In this case, we cannot show a reverse type this. The flow will be towards oxygen only. O negative and carbon positive. So these two are the resonating structure over here. And if you draw the resonance hybrid, this is partial negative charge and over here a partial positive charge. So this way we can draw the resonance hybrid, where the moment is being considered toward the more electronegative atom. The moment will be towards the more electronegative atom. I have shown you over here. The second type of moment which we are going to pi bond and positive charge. Pi bond and positive charge. So for a pi bond and positive charge, simply we can have a molecule like this. If we are having a molecule like this is a pi bond and this is a positive charge. So simply we can see this pi bond is going to move toward the more electropositive, but this carbon is more in the need of electron. So this will move like this and it became like this, and a positive charge over here. A positive charge will be generated at this carbon. So this is the resonance hybrid if you see over here. The moment of positive charge throughout over here. So this is the partial positive charge is being generated. The moment is from pi bond and positive charge. So one time the pi bond is over here, the coming over there, and the same way the positive charge is also being moved from carbon, let's say 1, 2, 3, 4, between carbon 1 and carbon 3. So the third type of moment which we can see over here will be for lone pair and positive charge. Lone pair and positive charge. Lone pair and positive charge. So this is CH. If this compound is having a positive charge, so this lone pair can also be transferred to this positive charge. A partial positive charge at this oxygen. So this is also a way how we can show this movement, and this is a lone pair and positive charge. In the same way, the pi bond and lone pair can also show pi bond and lone pair. If we are having this molecule, so what is going to happen? This pi bond, lone pair comes over here and this bond moves and became like this. So over here a negative charge generation, a new pi bond at this carbon, nitrogen, and a positive charge is being generated at the nitrogen. So NH2, this is again a partial positive charge generated at this carbon and negative charge at this carbon. If we are trying to draw the resonance hybrid, so this is NH2, and at this carbon we are having partial negative charge, and at this carbon we are having a partial positive charge. So this is the pi bond and lone pair. Lone pair and positive charge we have already been covered up. Lone pair and positive charge being covered up. So lone pair and vacant d orbital. Lone pair and vacant orbital. Lone pair and vacant orbital. So if we are having a compound like this, BS2 single bond NS2. So this is having a lone pair, and this boron it is having a vacant orbital. So in such type of compound also the movement of electron takes place, and we can visualize over here that this electron can come at this side, and we will get a product like BH2 single bond NS2 double bond at this side. So it is donating its electron a partial positive charge, sorry, not partial, the complete movement is being done positive charge, and over here a negative charge. So if you want to draw the resonance hybrid, so one of the important example of this is inorganic benzene. One of the important example is the inorganic benzene. Over there we see a lone pair and vacant orbital, this resonance phenomena. So another is like pi bond and unpaired electron. Excuse me, sorry. Pi bond and unpaired electron. So this is a pi bond, and if we are having an unpaired electron like this, so what will happen? I have shown you this example earlier also. This come over here, this goes over there like this. This is resonance structure 1, this is the resonance structure 2. And so in this case we can very easily understand how these various ways are I have shown you, through which we can draw this resonance phenomena. So initially I have told you why we need this resonance, because single structure, through single structure we were unable to know the properties of this organic compound. So that's why we have seen the delocalization of pi electron, only pi electron movement we have seen, not the sigma electron and atom. Sigma electron movement is termed as hyperconjugation, and hydrogen atom or any atom movement is termed as tautomerization. After that we have seen how these resonance structure are there. So some rules I have shown you, that net charge should be there, some stability thing we are going to pi bond. Another thing is pi bond and positive charge. Third is lone pair and positive charge, pi bond and lone pair. So positive charge and lone pair and vacant orbital, and the sixth is pi bond and the unpaired electron. So through which I have shown you how these different structure I have shown you. But through this different structure, we are going to see one more term, that is the stability of these resonating structure. Stability of these resonating structure, like we have drawn these. So which one is more stable? That the question arises. So which resonating structure is more stable? To understand this concept, there are few points which I am telling you. Stability of resonating structure. Stability of resonating structure. The first thing is neutral compound. Neutral resonating structure is going to be more stable as compared to the charged resonating structure. neutral resonating structure will be going to be more stable as compared to the charged resonating structure. So if you see an example over here, so these two are resonating structure. So this one is neutral and that one is charged. So this one is going to be the more stable. This one is going to be the more stable. The second is that is going to be almost similar to the first one only, more covalent bond. More covalent bond compound containing resonating structure will be more stable. So if you see here, we are having 1, 2, 3, 4 covalent bond, and in this we are going to see only 3 covalent bond. So these 2 points, they are only sub part of each other only. The third thing which we are going to see is like the more octet complete. If we are having some compound that octet is not completed, so those number of atoms, more number of atoms with complete octet, more number of atoms with complete octet will be preferred over here. And again the third thing which we are going to see over will be negative charge on electronegative atom and positive charge on electropositive atom. So those compound which are having those resonating structure which are having electronegative atom with negative charge is more stable, and those structure which are having electropositive atom with positive charge, they are also being considered as the more stable. And the last point I will just mention over here only, that is like charge away from each other and unlike charge closer to each other, unlike charge closer to each other. So this is the thing which we are going to show, and the next concept, the next detail which we are going to discuss in the next upcoming video. Thank you.